In this problem, initially we have a switch flipped over here to side A. So this capacitor is hooked up to the battery, charge is allowed to flow, and this capacitor is allowed to charge. And also initially C1 and C2 and C3 are uncharged. After this guy is charged, we flip the switch and then we let charge flow, and we ask what charge ends up now on each of the capacitors and what's the potential difference across each of the capacitors. So let's think about what's happening in this problem. In the first part of the problem, we have our battery here, and we have a connection to capacitor C1. So this is our 100 volt battery. This is our capacitor C1, which is 15 microfarads. And this part of the circuit that goes to C2 and C3, that's not connected at all. If this is not connected, if there's an open circuit, no current can flow in this part because it's not connected. So it's just like those two things aren't even there. So no current flow because the switch is open. So if we want to, we can work with this diagram, or we can simplify it to only have capacitor C1, because really, that's the only thing that's happening in the first part of the problem. So when the switch is in position A, we've got our 100 volt battery connected to capacitor C1. We know that charge is going to flow until capacitor C1 becomes fully charged, and then the charge flow will stop. So let's ask, initially, when the battery is connected to C1, what is the charge on C1? So what we know is that capacitance C is Q over V, which means that the net charge on capacitor 1, on this capacitor, is C times V. C is the capacitance, 15 microfarads. V is the potential, so if there's 100 volts on the battery, the 100 volts goes across the capacitor. So the charge that goes onto C1, once it's connected to this battery, is 1.5 times 10 to the minus 3 coulombs. So when we get started in the problem, this guy has a charge of 1.5 times 10 to the minus 3 coulombs. So that's our starting point. Then we flip the switch and we ask what happens next. So we flip the switch. Now our circuit looks like this. So there's our 100 volt battery, there's C1, the 15 microfarads, here's C2, 20 microfarads, here's C3, 30 microfarads. So now what happens? So if this switch is flipped over to here, there's no current flowing through this part. So there's an open switch on this side, so no current flow here. And then the next thing that we notice about this is that these two guys, we already know something about C1. Let's leave that the way it is. C1 has a charge, so as soon as the switch flips, C1 starts with a charge of 1.5 times 10 to the minus 3 microcoulombs. What's going to happen is that charge is going to flow. It's going to redistribute so that there's some charge on each of these capacitors. This starts off with a potential of 100 volts. That potential is also going to be spread over the 3 capacitors, and we want to figure out how much gets spread where. So the first step in this process is we know C1, C2 and 3 are initially uncharged, and they're initially connected in series. So if C2 and 3 are connected in series, we can find an equivalent capacitance of that series connection. When we add capacitors in series, we know we do 1 over C equivalent equals 1 over the first capacitor, C2, plus 1 over the second capacitor, C3, 1 over 20 microfarads plus 1 over 30 microfarads. So 1 over 20 is the same as 3 over 60. 1 over 30 is 2 over 60, gives us 5 over 60 microfarads. Of course, if you wanted to just do that in your calculator, it would be absolutely fine. So our equivalent capacitance then of 2 and 3 combined in series is 60 microfarads divided by 5, or 12 microfarads. Okay, so these two combined have an equivalent capacitance of 12 microfarads. Let's draw a new circuit and then let's apply what we think is going to happen here. So for our equivalent circuit, we have C1 here, we have a C equivalent here. C1 is 15 microfarads, that's given in the problem. C equivalent is 12 microfarads, we just figured that out. Capacitor C1, the charge is going to flow, so the charge is going to change. It's going to have a charge, let's call that Q1. It's going to have a potential, let's call that V1. The equivalent capacitor will now get a charge, we'll call that Q, and it will get a potential, let's call that V. What do we know about what's going to happen? The potential here is going to have to be the same as the potential here. So the potential is going to have to be equal all over. So the amount of potential here will spread to here. This capacitor essentially acts like a battery. So V1 equals V. And the net amount of charge on the two capacitors, Q1 plus Q2, or Q1 plus Q, has got to be whatever charge we started with. So we started with 1.5 times 10 to the minus 3 coulombs. That's how much we have to end up with. It can redistribute, it can go different places, but we have to have that same total. Okay, so now let's put this idea together, and then the last bit of information we'll use is that we know capacitance is Q over V, which means that potential V is Q over C. Okay, so let's put this expression in with this idea right here. So the potential across capacitor 1 can be written as Q1 divided by C1. And that's going to be equal to the potential across the equivalents, so Q over C equivalent. We can put our numbers in right here, but we'd be stuck for a second because we have Q1 and Q here, which is two unknowns. But if we look up here, we see that Q1 is equal to 1.5 times 10 to the minus 3 coulombs. Take away this charge Q. So let's sub that in right here. And our C1 is our 15 microfarads. And C equivalent is our 12 microfarads. This is an equation we can now solve, so let's cross multiply on both sides. Bring our Q term to the other side. So we multiply these two guys together, we get 1.8 times 10 to the minus 8 coulombs times farads equals Q outside of 15 plus 12 microfarads, so 15 and 12 is 27. So then our charge Q will divide both sides by 27 times 10 to the minus 6. Q is 6.67 times 10 to the minus 4 coulombs. Okay, so right now at this point, we could go ahead and find the charge on capacitor 1. So Q1 is the charge on capacitor 1, 1.5 times 10 to the minus 3 coulombs, subtract Q, 6.67 times 10 to the minus 4 coulombs. So the charge on capacitor 1 then is 8.33 times 10 to the minus 4 coulombs. We can put that up here. And then we can find our potential if we wish. Potential V1 is equal to Q1 divided by C1. That potential is 55.6 volts. Okay, so now we've taken care of C1. Next, let's deal with CEQ. What do we know here? Well, we know CEQ has a charge of 6.67 times 10 to the minus 4. And we know that this is a series combination of C2 and C3. So let's just back up our circuit a little bit. So we've got our C1 here, and that C equivalent was comprised of C2 and C3. Let's just remember about C1. So here's C1, 15 microfarads, 8.33 times 10 to the minus 4 coulombs, 55.6 volts. There's everything we know about C1. Here's C2 and C3. So the first thing we know is that these guys are connected in series. This is our series equivalent. Because all of these are series, they all have the same charge, and we already found that charge. So we know the charge on C2 and C3. Next, if we know the capacitance, and C2 is equal to 20 microfarads, and C3 is 30 microfarads, we can find the potentials. So the potential across capacitor 2 is equal to Q2 divided by C2. Q2 is the charge that we just wrote down that we found in the previous step. C2 is our capacitance, 20 microfarads. Remember that micro means times 10 to the minus 6. So the potential across capacitor 2 is 33.5 volts. Oh, 0.35, sorry. And our potential across capacitor 3 we can find in the same way, Q3 over C3. And that potential turns out to be 22.23 volts. So now we've found the charge on and the potential across each of our capacitors. We notice here that our potential adds up to be the 100 volts. So initially we had 100 volts. Now in the final step we still have 100 volts. So everything works out the way we expected it to.